get moving in a little bit. People still streaming in. As usual, if you got any questions, any kind, now's a good time. There we go. Oh, yeah. We have about another minute or so. Be good for folks to be here for this one. This is a sneakily important lecture. Okie dokie, I will get moving. Okay, let's see. What did we do last week? Last week was week 7, so that was apply functions, writing functions, that sort of jam. And so I think I mentioned at the end of week 6, maybe, that it's sort of, the class is sort of on a downhill trajectory as far as like trauma inflicted on you by the topics of the course. So loops tends to be the hardest on people, followed by the one on functions. And then after that, it's smooth sailing. We get into what I would call special topics. Today is going to be talking entirely about dealing with text data, working with strings, which is kind of a special topic and definitely would be a special topic if we were in sort of some general programming classes. But really, if you're doing any kind of work in social science data, you're probably going to work with a lot of text data. And so these are kind of key skills. And most of what I'm going to teach today, well, I wouldn't say most, but a lot of what I'm going to teach today isn't actually even R specific. It'll generally carry anywhere you want to go because just about everything uses regular expressions. Next week, we're going to do geospatial stuff. So we're going to do mapping and we're going to work with sort of geospatial data, make maps, work with stuff you might pull in from GIS software, that sort of thing. I use R as my main GIS platform, so you're going to get some of that stuff. We'll also talk about downloading like census data and working with that because it's just an easy thing to do in R. And then the last lecture will be sort of working with model results. So I don't teach any modeling in this class, really. I assume very minimal statistical training, but most of you are probably going to go take other classes that involve a lot of working with statistical packages. And you might want to pull those results out and do something useful with them. And what I found from having taken just about every CSSS class is that almost none of them actually show you convenient ways to pull out results from those methods and display them. And so I'm going to teach you ways that are way easier than what's usually taught in those classes to pull out things like counterfactual values, to put things in nice tables, that sort of stuff. And then I'll talk a little bit, well, actually, sorry, I will rant for about 30 to 45 minutes about reproducible research. And then that will finish us up. Okay, so today's about playing with strings. Okay. So the data I'm going to use in the lecture today is food safety inspection data from King County. So this is King County open data portal data. Unlike their elections data, these are actually fairly nice data. They aren't a complete mess. They are a little bit large and continually growing. So every time they do another inspection, it just gets tacked on to the end of this big CSV file. It's kind of big. If you're following along and you want to run things, you probably want to save this locally, load it from a local directory. You could load it directly like this if you want. It's perfectly fine. I'd still say save it to disk, maybe from the file, like run save on restaurants to somewhere. Okay. These data, because they're coming from a CSV file and they have a couple odd column types, I recommend also manually sort of setting their column types. If you're loading it in here, you can just use this right here. Yeah, that's all that's being done here. I'm loading these data in. So this is what the data look like. So as of the extract that I'm using here, which I actually haven't modified in a while, so it's probably about a year old, there are about 260,000 rows of inspections here. Each row is like an individual, not inspection, but an individual violation in the data. So it's about 260,000 violations. There's a lot of information in here. So something that's really nice about administrative data is it's often just jam-packed with all sorts of things that you might want to play with. So for instance here, right, we've got things like the name of the restaurant or establishment the inspection was at, or rather the violation was at, the date of the inspection, a description of the sort of the type of restaurant or establishment it is. Then it has things like the street address, the city, zip code, the phone number. We might use, we will use in the homework, the optional last homework in the class, the longitude and latitude to do sort of spatial mapping of food that will kill you. And then you've got sort of some other columns down here. A key one is the inspection score right here, which is sort of a point score where higher is worse violations, right? Yeah, so a whole bunch of things. And you get things like what are the actual violations that occurred, like non-food contact surfaces, food in contact with things I shouldn't be in contact with. Unidentifiable shellfish is a one that I always like to see in there, stuff like that. Random things, right? Food inspection data, okay? So we're going to use a whole bunch of these things in here and sort of play around with these data because they contain a lot of text entries we might want to do stuff with. Text entries being things like the names here, like at the Shack LLC. And you'll even see immediately the first entry in these data has a problem in this name. Do you see something weird and problematic about this name at the Shack LLC? It's minor, but it's dumb. Yeah, it's got a space for no reason, right? Maybe whoever input it added a space at the end by accident. Maybe another inspection for that exact same restaurant or whatever might not have that space and they wouldn't be grouped together if you grouped on them or something, right? Leading trailing spaces and things like that can actually mess up your stuff. Because to R, at the Shack, comma, LLC space has nothing to do with at the Shack, comma, space, LLC, no space at the end, okay? That space there means it's a completely different thing. Okay, so you might want to like uniformly get rid of these sorts of things. Another thing in here is like you'll see Seattle is lowercase. There's also uppercase Seattles. To R, lowercase Seattle and uppercase Seattle are totally unrelated things. Okay, if you wanted everything to be correct cities, you might have to turn them all to uppercase or lowercase. We're going to do all these sorts of operations. Okay, so strings, what we're going to be playing with today. So a string is sort of a general programming term for any unit of character data. A string is just a sequence of characters. So in R, we'll typically use a string or character data as sort of interchangeable phrases, but a string specifically refers to a single element of a character vector. Okay? So in other languages, string is often used to refer to sequences of numeric information, the most common of which are binary strings, like sequences of zeros and ones. We rarely work directly with binary strings or numeric strings like this in R. We will occasionally, but not too often. Okay. So the thing to note about this that makes these different from numeric data is that these are not single numbers. These are sequences of individual numbers. That makes them strings. You know something is a string, for instance, if a leading zero is meaningful. With a number, you could cut this zero off and you'd have the same number, right? It would just be like 1,110,000 or whatever right here. But a string, that leading zero conveys information. It's important. If you cut it off, it changes what the string is, okay? So if you have anything like that where a leading zero is in some way meaningful, it's not numeric data. It is a string of some kind, okay? Or it's some numeric data being displayed as a string. Like if you really want those leading zeros displayed in something in a paper or something, you're really gonna have to convert them to character first, okay? Zip codes are an example of this. We look at zip codes, we think of them as being numbers, but they are categorical data and their leading zeros are meaningful when they exist in the Northeast, right? You need to keep those zeros. If you convert them to numeric information, you lose your leading zeros. So keep these things separate. Okay. So is that clear on a string, what a string is? Nothing mysterious, just a bunch of text. We're going to play with text a lot. So some basic stuff on string manipulation. So we've seen the few functions I'm going to cover here for a minute. We've seen either in homeworks or in lectures, labs, things like that. I've used them before. So the first one that might be useful is the function nchar, n character, will get you the number of characters in each string in a vector. So here's an application of this. Say what I want to do is I want to check and make sure that all the zip codes in my data are proper sort of 5-digit zip codes. I don't want the full 10-digit ones, right? So I say here, take the restaurant's data and then mutate to create a new variable, which is going to be zip length, the length in characters of my zip codes. This is equal to the number of characters in the zip code column. And then I'm going to count this zip length variable, which is going to give me a frequency table of it. And we see here 258,629 zip codes are 5-digit zip codes. And the one zip code here that I added in to make a point has 10 digits. These used to have a whole bunch of 10-digit zip codes in it, but they cleaned it up right before the last time I downloaded the data. So I had to add one back in, okay? But there used to be like 10,000 of these like this. So this is just saying here, one of them has 10 digits. The rest of them have 5 digits. It tells us how many characters there are. So these are all length 5 zip codes, which is what we're expecting. Okay. So we might want to chop those zip codes down. Imagine, if you will, that there was more than one bad zip code, and we wanted to sort of make sure we got all the proper 5-digit zip codes and could throw away the rest of it. So there's a question here. Why do we need to change the zip code into a string? Well, the zip code is a string to begin with. You might store it as numeric data, which is bad, but it is in fact a string. The reason for it is that in the United States, in the Northeast, there are zip codes that begin with zeros. If you store it as numeric data, you will lose those leading zeros. They are in fact string data. There's something that always has 5 digits. Other examples of strings we tend to think of as numeric are things like participant IDs in a survey. Those are strings and they're not really numeric. Somebody who's listed as participant 15 is not somehow higher or lower than participant 14 or 16. It doesn't mean anything. It's categorical data or a string, much like a zip code. The fact that I live in 98105 does not tell me anything about like the numeric number itself doesn't convey some hierarchy of things. It's not like the people in 98105 are one stage higher in socioeconomic status from those 98104 people. Right? Okay, yeah, you'd never do math on them. Yeah, and character data is the same as string data. They're used interchangeably. Typically, a string is used to refer to a single element of character data, where character data is usually, character data being a plural term, usually refers to a bunch of strings. Okay. Yeah, this is all stupid nomenclature, but it's nice to know it and to kind of get used to it, so when you Google things, you get exactly what you want. In R, people tend to be fast and loose with this terminology, though. Okay, So what I want to do is I want to take these zip codes and I want to cut them down to only the first 5 digits. We can do this with a function we've used a bunch in this class, which is substring. I'm not using the stringer one here yet. I'm going to show it in a minute. But the base R version of substring is just substring. And what we can do is we can say, I want to modify my restaurant's data. That is, I'm going to assign some changed version of these data back to the original. Take the restaurant's data and then mutate and create a new variable. I'm going to create the zip5 variable, which is equal to a substring of the zip code. I want to start at the first digit or value, the first character of the zip code, and go to its 5th. So if there's anything longer than 5 digits in the zip code, it's going to chop them off. If you had a whole bunch of 10-digit zip codes, this would discard all those extra digits. Okay. This assigns it to zip5. I could then say, give me the restaurants, give me their distinct zip codes, and give me the first 6 observations. We see here now all of our zip codes here are proper 5-digit zip codes. So I fixed the one bad zip code. Okay, does that make sense, the way substring works? If this is any number of digits, it doesn't matter. It's going to pop out as being just the 1st through 5th digits of this thing, or letters or whatever. Okay. Next, paste. Paste is another function we've used a lot, paste and paste 0. Something you might want to do is use all the different columns in this data set to put together a mailing address. You might actually do this for something if you're like working on a, say like administering a survey, and you actually need to generate the list of houses you're mailing this thing to. You might do this programmatically, right? So here's an example. I'm going to take the restaurant's data and then mutate a mailing address column, which is equal to pasting together the address, comma, space, the city, comma, space, Washington, space, the 5-digit zip code. And I say I don't want there to be a separator, so blank. So this makes this function the same as paste 0, but I'm just showing you can do it either way. Now, if I say take the restaurant's data, get distinct mailing addresses, and look at the first 6, we see here that it's constructed a mailing address. 2920 Southwest Avalon Way, Seattle, Washington, 98126. So 2920 Southwest Avalon Way is the address. Then there's a space or a comma space. The city of Seattle is the city, comma space Washington space, and then the 5-digit zip code. So I've just assembled a mailing address by pasting together a bunch of columns. Okay. You might want to do this for a variety of reasons. One common usage of pasting together multiple columns is if you have something like, let's say you have a survey that has like a neighborhood ID, a household ID, and a person ID in different columns, and they don't uniquely individually identify it, you could paste them all together into one ID that uniquely identifies each row in the data. I do this all the time with nested surveys. A lot of reasons you might paste stuff together. Does that make sense? Not too bad. Okay. Wouldn't you want to rectify the spellings of Seattle before doing this? Yeah, quite possibly. And it's actually visible here. So you'll see Seattle lowercase, Seattle uppercase. This is stupid. This is a data quality issue. Yeah, normally I would want to, but the reason I haven't is because the function I'm going to use to do this is in the stringer package, which I haven't shown yet. Well, I've shown in class repeatedly, but I haven't shown in this lecture yet. But yeah, I would fix all these things first, right? Okay. So paste 0. Paste 0 is just a shortcut for paste without a separator, right? So let's say I take something like this. So this is a vector, the numbers 1 through 5. This is the letters A through E. So it's the lowercase letters of the English alphabet, the 1st through 5th, right? If I say paste these 2 vectors together, it's going to paste together 1A, but with a space in between them, because that's what paste defaults to, 2B, 3C, 4D, and 5E, right? So the way paste works is like any other sort of vectorized command in R. If you give it something that's length 5, it's going to output a length 5 vector. Okay. If I did a length 5 thing here and a length 1 thing over here, like I did 1 through 5 in the letter A, it would recycle the letter A 5 times and make 1A, 2A, 3A, 4A, 5A. It does vector recycling like every other thing in R. Okay. So by default, paste separates things with a space. I could instead run the exact same command here, but say separator equals nothing. And it gives me the same result, but with no space between the values. I could save myself from typing comma space separator equals nothing and just say paste 0. And this command give me identical results. Do it either way, do whatever you remember. I always just remember to do paste 0. Okay, make sense? Nothing we haven't seen before. Okay. So the thing is I've only shown you basic uses of paste. Paste can do a lot of other things in weird ways and in weird combinations of weird ways, okay? So the idea with paste is that the separator command or the separator argument will control what happens when you do entry-wise, I say, squishing of vectors. So when you have one vector here and another vector here and you squish them together, it controls what goes in between those things. There is another command I've used in lab, but I haven't used in lecture called collapse. Collapse will control how these things you paste together instead get converted from a vector into a single string, right? So no matter what its length would have been, it will end up length 1. Okay? Here's some examples to illustrate how separator and collapse work. Okay? So what I'm doing here is I'm saying I want to paste together the first 5 letters of the English alphabet. But instead of saying separator, I say collapse on exclamation point. The result of this is a length 1 vector. So instead of giving me something length 5 like its input, it collapses the entire thing down to a single element. And in between the letters, it puts exclamation points, the thing I've collapsed on. Okay? This is a very different thing than pasting things together into a length 5 vector. This collapses stuff down. So if you have some like long vector of text and you want to make like a single sentence out of it or something, you would use collapse to do that. Here's another example. If I say paste together 1 through 5 and the first 5 letters, separator equals plus, this instead of a space has a plus in between all of them. Okay? I could say paste 0, so there's going to be no separator between things, 1 through 5, letters 1 through 5, but collapse on something longer than a single character. I end up with a length 1 output, but you see what it's done. It's first pasted together the number 1 in A, the first element of this and the first element of this, then 3 question marks, then the second element of this, the second element of this, and then question marks. Okay? This is sort of an odd behavior, but there might be cases where you want to construct something this way. In other words, I'm sort of mixing together some kind of separator, absence of separator, multiple arguments to paste and collapse. Here I've said paste together 1 through 5 and the single letter Z with a separator of star, and you'll see it recycles Z. So I get 1 star Z, 2 star Z, 3 star Z, 4 star Z, 5 star Z. So this has been recycled to be the same length as this, and then it's just pasted them together. The last example is doing both of these things at the same time. I'm saying paste together 1 through 5, the single letter Z, separate by a star, collapse with a tilde. I get this wonky thing where you see what it does. It combines 1, puts the separator in, then the letter Z, and then the thing to collapse on, and then repeats this over and over again. 1 star Z tilde, 2 star Z, so on and so forth. Okay. There are times you might want to do these sorts of operations. An example might be if you want to generate a statistical formula based on columns in a data set, you could extract the names, collapse on them with plus signs, and it will string them together. I've done that before. You'll figure out reasons to do it. So just sort of look at these things, try and understand how they work, play with them if you're not sure. But there's a lot of different ways to put text together and sort of mash it together in R. Okay, any questions on that?
I just have a quick clarifying question. With separate, they would still be different vectors. It's only collapse that collapses into one.
Yeah, so this is a length 5 vector, so it has 5 elements. And then this is a length 1 vector. It has a single element. So collapse reduces it to 1 element. Just using separator keeps it the same length as its input. Yeah. So another question, in the final one, does the sequence matter? The sequence of 1 through 5 in Z matters. If I put Z first, it would instead be Z star 1, Z star 2, but the sequence of these things does not matter. If that makes sense. Okay. So next thing I want to move on to is the stringer package in R. If you've watched The Wire, you know my joke. If not, it makes no sense, and it's just a picture of Idris Elba. Okay. The stringer package is the string manipulation package in the tidyverse for R. Okay, so this is another package like most of the main stuff we've been using in this class: ggplot, dplyr, tidyr, lubridate, reader, right? So stringer does what a lot of these other packages do. It sort of supersedes base R functionality with more intuitive, easier to use, sometimes more powerful functions with sort of a uniform interface. Okay. Main things that stringer brings to the table is it does replace some of the basic string functions like paste and end character with alternate functions that have slightly more intuitive behavior or good built-in error messages. It also adds functions to do things that are harder or annoying to do in base R, like removing white space or adding white space to pad things. And most importantly, and what we're going to dwell on today, is things to perform tasks related to pattern matching. That is detecting, locating, extracting, matching, replacing, and splitting text based on search terms. So these functions will use regular expressions to describe patterns in the text to go and locate things to do operations on. There are ways to do this in base R and also in the stringy package, which is sort of a powerful, hard to use package for string manipulation, but those both suck to use. So most people use the stringer package. One really nice thing in the stringer package is almost all the functions in stringer begin with the text str_. So when you want to use a stringer function and you're in RStudio, you can type str_ and then bring up the autocomplete menu and search for the function you want. There's a lot of them. It's easy to forget them. Why not just search for them instead of trying to memorize all of them? You'll inevitably memorize the ones you use a lot, but there's no reason to try and memorize everything. Okay, so we load it up. Let's do some stuff with it. First thing is I want to show you some equivalencies. So these are just functions in stringer that work basically the same way as the base R ones, though sometimes they augment them a little bit. One example, which we've used a bunch in this class, is string_sub, the string sub function. This works basically like base R's substring function, but it adds one important, powerful thing. The normal substring function doesn't allow negative indexing, but string sub does. Negative indexing allows you to search not just from the beginning of some text, but counting backward from the end of it. So in this case, let's say I just want to take the word here, the proper noun Washington, and for some reason I really want Washington. So I'm going to take the first character all the way to the third from the last character, which is T. So this says let's begin at 1, which is this one, but we're going to end at -3. This is -1, -2, -3. So it's going to read in 1 through -3. Being able to count backwards from the end allowed us to do that handy thing in the homework of cutting off .csv off of file names when all the file names have different lengths. This is really useful. You can't do it in the base R one, so you have to do one really annoying, stupid thing. If you want to count back from the end, you actually have to reverse the characters, count forward to what you want, slice it off, and reverse them back. That is actually what string sub is doing under the hood, but so it goes. Okay. Another thing, string C. String C is string combine. This is a analog. It's basically identical to the paste function. It takes, however, a separator argument like paste, but when you don't give it a separator, it defaults to being like paste 0. This gives you the best of both worlds. It doesn't assume you want a space in there, but you can use a space if you want. So technically speaking, I consider this strictly superior to paste 0, but it's really easy for me to remember I want to paste stuff together. String C isn't the most obvious name, and so I forget about it all the time. Okay, but basically it works like paste 0. Okay, other things that are equivalent. The string length function is exactly the same as the end character function. If I don't know how many letters there are in the word weasels, I now know there are 7, and I can do it 2 different ways. It's the same as end character. Don't think it has any additional options, so it's really just like an alias.
Why would they go to the trouble of making that?
Why would they? Just I think so that you have it as a one-stop shop. It's one of those things where I think they're just like, it's a common operation, so they provide it. But it doesn't, I don't think it really does anything else. Now I'm curious. No, it literally does nothing else. Oh, end character actually does more things.
So there's no version of RStudio that doesn't have ncar, right?
Correct. End character is a base R function. So you see it's in the base package. It's literally always there.
I don't understand why they would make that, but I guess it doesn't really matter. So
yeah, it is kind of an odd thing. Number of code points in a string. The real question is if it has any kind of alternate functionality. I would actually have to verify in weird edge cases if it works in slightly different ways. Let's see. Yeah, it might behave slightly differently. That's interesting. So it might actually behave differently on Unicode due to a different number of code points. Who knows? Okay. So questions I missed here. Does string have the collapse similar to base R? So like in string C? Yes, it works exactly the same. So it has a collapse argument. And it's actually not more useful in pipes because it's exactly the same function. I suspect that the reason to use it is it might behave differently with Unicode. So for instance, Unicode might detect, so here's an example. If I say, yeah, that'll give me string length 1. Will end character to give me that? Oh, they still do the same thing. Nope, no idea. I have literally no idea why you'd need an alias there for that. And if you're wondering why that returns a length of 1 instead of a length of like 6, that is actually because this right here is one character. It's a Unicode character for a particular symbol, which it will not automatically get converted. Oh, it does. There's an umlaut. Unicode. Okay. That's the end of your tangent for today. Okay. So, yeah. Now we're going to get to those functions to clean up and fix things, right? So these are functions which do have equivalents in base R and stringy, but they're slightly more annoying and there's fewer of them. So Maybe you want to do something like convert all of the text in a variable to uppercase, lowercase, or title case. There are convenience functions in Stringer to do this. This is something that I highly recommend doing. Anytime you're working with text data, you need to do cleaning with it, you care about it, pick one, convert everything in case. Because if you don't, you end up with stupid shit like this. So here I've gotten the first 6 unique values of the restaurant's data city column. We see things like Seattle and Seattle being treated as 2 different values when they are in fact the same city. We have lowercase Issaquah over here. There's probably lowercase Bellevues and Kenmores, right? These are the same city, but because the data have been entered in uppercase and lowercase separately, who knows? Maybe there's even a lowercase S1 working in there somewhere. We probably want to fix all of these things, right? So what we can do is say, take the restaurant's data and then mutate, in this case, this problem with these identical what should be identical values having different cases. This could be every character column in the data set. I'm just going to go ahead and fix all the ones I care about. Let's mutate across multiple variables, the name, the address, and city columns. Let's convert them all to uppercase. I look at them and now everything is beautiful uppercase text. I say pick one, use uppercase or lowercase, but you do you. Next question here. If we have the string hello world, will title case capitalize one or both words? The answer is, I believe, both, but let me verify that. I can't spell hello. Yeah, so that does that. If you want to do only the H, you would say string sentence, and it would do that. Yeah. Well, no, it's actually better that I check it so that everyone else can see the demonstration. So might as well just have me run. Next one. Might have mentioned this, but I forgot. What's the difference between unique and distinct? Oh, that is an excellent question. Unique only works on vectors. Distinct works on a data frame. So you'll see what I did here. Here I said head unique on restaurant's city. So if I wanted to do the dplyr version of this, I would instead say restaurants pipe to distinct, and I'd say distinct city. But distinct is actually taking the data frame as its first argument and city as its second argument, whereas unique only takes the vector. Yeah. Does that make sense? Great questions. Okay. So this is straightforward. One of the first things I would do most data cleaning things with text data, convert cases. I usually work in lowercase everything, but do whatever. Or sometimes I'll actually carry some meaning with upper and lowercase, but not too often. Okay, here's another thing that you might encounter. With text entered by humans, it's very common to have leading or trailing extra white spaces in your data. White space just being a space character, right? So for example, if I get the first 6 observations of the unique values of the restaurant's data's name column, so it's the name of restaurants, in this case, actually I got the first 4, we see that one I pointed out earlier, at the Shack LLC space. Maybe I want to chop these spaces out just to make sure if this thing is in here again, there isn't one without the space, right? So any character column in my data could be affected like this. That is, it could have this symptom of extra white spaces. So I'm going to go ahead and get rid of them in all cases. We're going to do this using a function called stringtrim. What stringtrim does is it just removes any spaces at the beginning or end of a string, but leaves all the other spaces alone. Okay. So I say here, take my restaurants data and then mutate across the columns where those columns are character data. So this is a way to select every column in your data set that is a character data column, and then apply to it the stringtrim function. So this is going to go through my data set and grab every character data column, the name and all that stuff. It's going to give it to stringtrim. Now you can see if I get the first 4 unique values of the restaurant's name column, at the Shack LLC no longer has a space at the end, but everything else has stayed the same. It hasn't gotten rid of spaces in the middle or anything like that. Okay. This is another common sort of cleaning thing you might do. You might lowercase or uppercase your stuff, trim off extraneous white space. You might also remove special characters and stuff like that. You sort of cleanse everything to get it down to what you want. Does that make sense what I did there? Any questions about that? Including about the mutate across where? Yeah, I'm absolutely happy to. And I was kind of surprised somebody said, didn't ask me, what did he just do? So, okay. So what I'm doing here is I'm taking advantage of some of dplyr 1.0's new functionality, which replaces functions like mutate, at, and if to work over many columns simultaneously. So normally in mutate, you create like one variable at a time, okay? Well, the across function lets us create or modify multiple variables simultaneously. So this is saying I want to work across multiple columns. This is going to modify multiple columns at once. Normally, instead of this where is character, I would do something like C, and then in the C, the vector, I would have a bunch of column names. But instead, I don't want to name all these columns. I instead want to say, I want R to go and figure out what columns I want. I'm just telling R that I want all the character data columns. If you're working with a data set and you look at the classes of the columns of the data, so you like glimpse or something like that, you'll see character data. What this where is character is doing is it's going to select which columns go into this across function in mutate based on whether or not they're character columns. So you can imagine what it's really doing is it's going to go across every column in the data set running the is.character function. Is.character returns a true if it's character, false if not. Basically what happens is wherever it encounters a true, a character column, it keeps that column name and it puts it in across here. And then it's just going to mutate over all of them. Another great question I have here is why do you have the tilde there? So there's 2 ways I could write this exact thing, or the 2 ways I could write this thing the same way. I could say like that. I could say, take the restaurant's data, mutate across all the character columns and run the stringtrim function on it. I could also say, do this exact same thing, tilde stringtrim period. This looks slightly more straightforward. This down here is a more complex way of doing it. The nice thing here is this second way lets me add extra arguments to my functions. Up here, I don't have any parentheses, so I can't add extra arguments to them. So this is a more flexible and powerful way to do it. This is something called a dplyr lambda function. So if you ever need to Google for it, this is a type of lambda. It's the way you write anonymous functions in dplyr. This tilde is basically taking the place of function x. It's actually, technically speaking, it's doing function period. So you could also write this basically like that, is what it's doing for you. It's a way to do an anonymous function. What's important is not understanding what it's doing, but understanding how to use it. And you'll get the intuition for sort of how it works more by using it than by explaining it verbally, which if anything is likely to confuse. Next one. Is there a way to use across while skipping certain columns, i.e. you have binary data, but some columns are not? So across, if you want to, so it depends what you mean. So do you have specific columns you want to get? If you have a list of specific columns, you could provide the exact columns. But if you're saying you want to go across like all your character columns except one, you would have to, you could subtract that specific column. I think you do that like don't do the name column, but do the rest of the character columns, I think would work.
Yeah, thanks.
Yeah, I think that would work. I would have to look at it.
Okay, yeah. But the minus, the minus thing helps. Yeah, I forgot we could do that.
Yeah, for sure. Okay. Destroy. Okie dokie. So we can trim out white space. There's also another one I don't think I mentioned in here, that if you want to get rid of duplicate white spaces inside, like let's say you're working with an R&D document that was originally your advisor's Word doc, and he's one of those people who puts 2 spaces at the end of every sentence, and you must destroy that as quickly as possible. You can use the string_collapse function. I think it's string collapse, and it will take out like double spaces if you want. Okay. The reason you don't have to put double spaces at the end of sentences anymore is the word processors do it automatically. Like you'll notice the spaces are actually wider after them anyway. Anyway, so great one. LaTeX also does it automatically, so you don't have to put them. So literally any typesetting thing other than a typewriter takes care of doing this for you. So you don't need to do it. So my advisor does it, and I'm constantly like messing with them and whatever. I just replace them at the end. Okay. So regular expressions and pattern matching. Now we're going to get into the simultaneously more complicated, but also drastically more powerful part of this lecture. Okay. So what are regular expressions? Regular expressions, or regexes, are a logical language for describing patterns you're looking for in text. This is a way to tell a computer what you're looking for. It's very easy to describe to another person what you might be looking for in a sentence. Like if you say something for, find the word right in this paragraph, but only where it occurs after the word we. That's pretty easy for humans to understand. To be like, okay, I'm looking for right after we, boom, it's right there, right? How would you convey that to a computer and say, I want to find right that only after we? Well, you'd use regular expressions to do it, okay? The way regular expressions work is you will write some expression, which is essentially a type of sort of logical test. You'll apply it to some string input, and then it will return the things that match the expression, okay? So it's essentially like something returning a true, but it pulls the actual string as a result rather than the true. Okay? It's kind of like things we did where searching with equals equals and stuff. And then we do operations with what we get. Okay, so there's 2 things that regular expressions are made of. There's 2 types of things you give them. There's what is referred to as literal characters. The literal characters are the snippets you actually want to search for. If you're searching for the text SEA, like we did in homework 5, you'd say, I want SEA or SEA space. If you're searching for the number 206, you just say 206. This seems obvious. If you're Googling SEA, you can type in SEA, okay? The real magic and also horror of regular expressions comes in the meta characters. Meta characters let you be flexible in describing these patterns and be more specific about things. Meta characters include lots of different things. Backslashes, carets, dollar signs, periods are a meta character. If you want to search for a period, you can't just put period. There's also pipes, parentheses, brackets, squigglies, you name it. These are all meta characters that give your regular expression rather, some special instructions on how to behave. Okay. If you want to treat one of these meta characters as a literal character, that is, you actually want to search for a parenthesis, you have to escape it. Escaping a character just means putting 2 backslashes in front of it. In some other languages, it's a single backslash, but in R, you got to use 2. So if what you want to search for in your text, let's say you want to find the actual characters, parenthesis 206 parenthesis, including the parentheses, the thing you're going to search for is backslash parenthesis 206 backslash parentheses, because these backslashes say the thing that follows them, I want to search for that. I don't want to use the parentheses as a special meta character. So here is an excellent question in chat. So how would you then search for 2 backslashes? Okay. So you have to escape the backslashes. So if you want to search for them, it's actually going to be, so let's say I have the actual text. So it should be the actual text 2 backslashes, but I want to search for that. Well, that I'm not. Okay, that does do it. Okay, so you've essentially used this backslash to escape this backslash to escape this backslash. So you'll use 4 of them. If you don't, it's going to yell at you like this. You got to do all sorts of lots and lots and lots of backslashes. Yeah. So this, of course, explodes out of control if you need to search for lots of slashes and things. So it goes. Excellent question. Okay, so let's start using all these stupid symbols in rapidly escalating examples. Backslashes only need 1 backslash each rather than 2. Yeah. So what's happening is you are using the backslash to escape the backslash, which then displays a single backslash. But in a regular expression, the backslash is also a special character. So you actually escape the thing that creates the escape, and then you escape an escape slash. So it gets kind of out of control. So this right here, so as an example, right here, this text, this shows me these 2 slashes, right? If I only have 1, notice how it's yelling at me and doing a plus. That is not a complete statement because this backslash right here just escaped this quote over here. So it does a different thing in a string than it does inside the regular expression, if that makes sense. In the regular expression, it's a meta character, so I technically need a whole bunch of them to do this stuff. This here would be a regular expression. This here would not actually search for a literal slash. If I want to search for a literal slash, I have to do a lot of mojo. I would recommend playing with these and you'll start to get a feel for it. It's hard to explain. Searching for backslashes gets really annoying. Okay. Next. Oh, actually, let me see. Does cat behave? Oh, there we go. Yeah. Look what happens if I cat to print that. 2 slashes do not come out. A single slash comes out. This text with 2 slashes is literally a single slash. Okay. So this is the problem that's going on, is to generate a slash in text, you have to use another slash. And that's what's actually being fed to the regular expression, if that makes sense. Yeah. Okay, so let's do something. So what I want to do here, I want to get the health code inspection data only for coffee shops. I'm going to say, as a primitive search, that a coffee shop is anything in my data with a name containing coffee, espresso, or roaster. There's many other possible things, but I'm just going to go with those. So the regex to search for any one of those things is coffee or roaster, or espresso or roaster. Because the vertical bar is the meta character that means or. Conveniently, it's also a character that means or, like in filter, so you've seen it before and it's an intuitive example. What I can do is I can use the string detect function. The string detect function will return a true, so it's going to return a logical vector of trues and falses. It returns a true where it detects coffee or espresso or roaster, and false where it doesn't see any of these 3 words. Okay. I can use anything that generates trues and falses in filter. So if I want to subset my restaurant data down to just the coffee shops, I can say, take the restaurant's data, and then filter down to the rows where string detect on the name of the restaurant contains coffee, espresso, or roaster. This is going to return a true wherever it finds one of those words and a false where it does not, and thus yields only the coffee shops in the data set, assuming this has been a good measure. I then take my coffee data, go to the distinct names, that is distinct restaurants, get the first 6 observations, and it has returned to us Two Sisters Espresso, 701 Coffee, 909 Coffee and Wine, AJ's Espresso, Alki Homefront Smoothies and Espresso, and All City Coffee. These look like coffee shops, so this seems to have done a pretty good job. If you needed to perform a similar operation, like you want to get down to rows that only contain some word, this is your way to do it, right? String detect is a very handy function for subsetting data when you don't have some variable that like numerically indicates it, you need to hunt around in the text. We have questions on that? String detect is pretty straightforward, and this is a very easy regular expression, but it kind of gives you an idea what's coming. Yeah. Nothing. Could I write coffee or espresso like that? The answer is no. Okay, so the issue is that the regular expression must be a single string. It doesn't take multiple strings. So the issue here is if I put quotes around coffee and then put the or bar, I would have a string here and then an or in another string, and it doesn't know what to do with that. The entire regular expression must be a single quoted string. Was that the question, or was I answering a different one? Yeah, so it doesn't also, as for the next one, if I'm understanding what you mean, it doesn't see the bar here as a literal character. It interprets it as a meta character, meaning I want this thing or this thing or this thing. So it doesn't search for the bar, it just interprets it a different way. You could imagine what it's doing is it's basically converting these meta characters into, like, you could imagine converting them into English, and it's literally reading coffee or espresso or roaster. The ors aren't important, but it's saying I can have any one of those things. It's kind of like doing the filter statements, but it's all in one block. The reason they're all in one quoted string like this instead of broken up separately is actually because R is passing this single string to another programming language with a library for processing regular expressions, because basically every other programming language out there runs this through its own separate regular expression libraries, so, which is way too much information, but that's what it's doing. Okay, so that answers those questions? Oh, here's another one. How is string detect different from contains? This is an excellent question. Contains is used in the select function and is used to locate variables. String detect is typically used in a filter statement to select rows. If we wanted to select columns that match something, we would use the matches function in select. So for example, let's say I have the classic MT cars data set. MT cars has columns that look like this. Let's say what I want to get out of here is I only want to get out the columns that contain an A. I could say select matches A, and it's going to give me the column drat, AM, gear, and car, because they're the only ones that contain the letter A. So I can use this for selecting columns, but it uses its own separate functions. If that makes sense. And you can use regular expressions in here, which I'll show. Like, for instance, maybe what I want is I only want the variables in here that begin with the letter A. I could say caret A, and that would give me only things that begin with the letter A. So you can start playing around with regex inside of matches. Contains doesn't allow regular expressions. It's more limited. If I do contains, it's going to give me nothing because it doesn't know regex, but it's okay with contains an A. So contains is a more primitive version of matches. Next one, if you want to look for two words like coffee shop, could you do roaster or coffee shop? Exactly how you would do it. So you'd say like string detect name, and then I'd say like roaster or coffee shop or espresso. and it would recognize coffee shop here as one entire string to search for. Because it treats spaces as a literal character. Yeah. Yeah, fun stuff. Did I miss any questions? Go Beans. Okie dokie. So we're starting to get somewhere. So maybe I have a question like, will my coffee that I drink kill me? Let's make use of these inspection scores. So I say here, take the coffee data, select down to only the business ID, name, inspection score, and date. I'm going to group on business ID, filter to the most recent date, the maximum date. So this is going to give me the most recent inspection for any given business. Take only the distinct rows. Then I plot my inspection scores, do a quick histogram. Okay. As I said earlier, the inspection scores are essentially a count of health code violations. So if you are getting coffee at a coffee shop, a place that serves coffee, and somehow manages to get 40 health code violations, you maybe don't want to drink coffee there. Okay, that is a lot of health code violations for a cafe or something. So just a thing to know. Honestly, some places with a lot of health code violations, I'm not going to stop eating there because they're delicious, but still, you know, it's good to be aware. It's good to know where you're getting placed. Okay, let's do something else with string detect. Maybe what we want to do is we want to get the phone numbers out of our phone number column, whose first 3 digits are 206. The thing is that sometimes there are 206s with parentheses. Sometimes there are 206s without parentheses. Sometimes these 206s are followed by a space, and sometimes they are not. When you're working with something like this, a process I recommend doing is try and create a bunch of examples quickly to run your expression on to test it instead of the entire data. So the idea here is I want to be able to correctly pull out the 206 number from a number that looks like this: 206, 1, 2, 3, 4, 5, 6, 7, parentheses 206, parentheses 206 followed by a space, but I don't want to get the 206 out of the middle of this one here, right? I want my regular expression to find this one, and this one, but not this one, okay? So how am I going to do this? I'm going to do it with a regular expression that looks like this. This is caret backslash backslash parenthesis question mark 206. Okay, this is already starting to look angry and something you don't want to deal with, right? Let me explain this carefully, what's going on. So I used this a minute ago when I was searching for variable names. The caret meta character here, which is can be found if you hit Shift-6, it's the exponent sort of operator there. This says start looking for this pattern only at the beginning of the string. Whatever follows it must be at the beginning of the string. Okay. Then I write backslash backslash parenthesis question mark. So if you remember, parentheses are a meta character. If I want to search for a literal parenthesis like this, I need to escape it. To escape it, I put 2 backslashes in front of it. And now backslash backslash parenthesis will look for a parenthesis. The thing is sometimes there's a parenthesis and sometimes there's not. So question mark makes it optional. This says if you find a parenthesis at the beginning of the string, match it and that's good. If you don't, it's okay. I don't require it. I merely permit it. Okay. Next, the 206 here is the literal string 206. So if I read this again, you can say at the beginning of a string, look for an optional parenthesis followed by a 206. So this is going to allow one of 2 things: parenthesis 206 or just 206 alone. Either way, they have to be at the beginning of the string. If I run these examples here, I do string detect on my examples using my pattern. I get true, true, and true because it matches these 3. and I get false here because it fails to match to this one because the 206 does not occur at the beginning of the string. Okay. So here's an excellent question. If we were aliens that sometimes use double parentheses 206, would we use caret that? The answer is close, but not exactly. What we would actually do, annoyingly enough, we would do that. Because remember, we got to escape the parentheses. So this would say, look at the beginning, optionally have one parenthesis, optionally have another parenthesis. So there can be up to 2 parentheses and then a 206. Yeah. So here's an excellent question. What if we want to look only at the end of a string? The answer is $, which we're going to use in a little bit. If you want to look at the end, so we want numbers that end in 206, I would instead say $206. So this would say, look for the number 206, but it must be immediately followed by the end of the string. This would get all the 206s at the end and nothing else. So caret and $. They're 2 of the most useful regular expression meta characters. We'll use $sign in a bit. Okay. So, any more questions on this one? I'll keep escalating these examples. They'll get wild in a minute. And a sort of a general answer to a question you might be wondering, no, I do not memorize all of the meta characters for regular expressions. You'll find a few you use commonly, and otherwise you look them up. There's a lot of great resources on how to do regular expressions, Google and things like that. Don't try and memorize them all. You get some old arcane programming wizards who truly know all the regular expressions. They just answer your questions on Stack Overflow. You don't want to be those people. Excellent question. Are they the same across all languages? Basically, yes. Nearly every programming language uses by default a regular expression library that uses basically this exact same syntax. The main difference is escaping things. Often in other languages, you often only need 1 backslash. R needs the second one to escape its slashes. But in general, everything else is the same. There's different flavors of regular expressions, but by and large, you learn one of them, you'll be able to do it in anything else. It's kind of universal, which makes it one of the most useful things you can learn in this class. If you start to master them, you go and learn any other language, you can take 100% of your regular expression stuff and pass it out there. Using regular expressions in like SQL, it's the same shit. It's all the same regular expressions. So everywhere you go, it's all the same. Python, SQL, I think the SAS even uses normal regular expressions, you name it. Okay. So here's another useful function that might be illustrative for how these regular expressions work. Stringer has a handy little function built in called string view. This opens up a viewer pane in our studio to show you what text is being selected with your regular expression in whatever string you're working with. I'll show you an example. So earlier I had my area code 206 pattern to get the 206s. Let me populate it here. This is what it was actually highlighting. I don't think I can zoom in here. No, I can't. Might be a little small, but basically this shows what my regular expression highlighted. It found 206, it found parenthesis 206, it didn't find the 206 in here. So string view lets you actually kind of on the fly display and see what your regular expression is selecting. So if I close this and swap to something else, let's string view, let's go with the number 4. I'm just going to string view 4. You'll see now it's highlighted all the 4s in here. So this shows you what the regular expression will find in whatever text you give to it. So if you're curious whether you're getting what you want, you can use string view to play with it. Handy and dandy. Can you do string view for positive matches only? What would the negatives look like? Pattern match equals NA. Shows only the strings that don't match the pattern. So it looks like you can do that. Everyone matches that. So let me Okay, that lists only the non-matches. So string view by default would sort of display whether they match or not. True will display only the ones that did match and what parts of it they matched. If you're looking for highlight the things that don't match, it doesn't appear to be able to do that, but you could invert your regular expression. I just don't remember offhand how to do a reverse expression for the entire expression. Yeah. So I never do negative matches. Okay. So let's apply this. Maybe what we want to know is how many phone numbers are or are not in the 206 area code. I might say, take the restaurant's data and then mutate a new variable. The variable is going to be has a 206 number. This is going to be the result of string detect in our phone numbers. Look for the area code 206 pattern I used before. And then I'm just going to count whether they have a 206 number or not. This says 66,000 do not have 206 numbers, about 110,000 do have 206 numbers, and I get a missing value for about 83,000. Basically, a regular expression cannot search in a missing value and will return an NA for string detect. So these are ones that did not have a valid phone number, so they've got an NA there. Can't search, returns an NA. Okay. So this might be how you'd use string detect to generate a new variable. This is just a binary variable. Okay. 1 second. It's very hot in my room. I'm going to slightly crack my window door. Please breeze, kick up. Okay, there we go. So next function I want to talk about is string extract. So string extract kind of works like string detect in that it finds the matches, but instead of returning a true or false, it pulls out the thing that matches and gives it to you. Okay, so something we might want to do as an example is I want to use this to extract the directional part of a Seattle address. If you've ever seen, Seattle addresses, for those of you, I mean, God only knows, there could literally be people here who've not yet moved to Seattle to go to the university. We've been in pandemic mode a long time. Seattle uses directional addresses. If you see a street and you see north, northwest, southeast, you actually know where it is in the city already because they're sort of there's not 9, but there's 8 sort of sections to the city: north, northwest, southeast, so on. So there's useful information encoded in the addresses. I might do something like this to extract only the directional component of a street address. I'm going to say my direction pattern is this terrible mess, which I'm going to explain in a minute. To give you an example of what I want to extract, here's some addresses as tests. I've got 2812 Thorndike Avenue West. The only thing I want here is the west, right? 512 Northwest 65th, I want the northwest. 407 Cedar Street doesn't have a directional, so I don't want it to return anything. 15 Nickerson Street has nothing. I don't want it to return anything. So you see why this is complicated. The west can be at the end, a northwest can be in the middle, right? They can be all over the place. So I can't just say, look at the beginning of a string, look at the end of the string. Instead, I have to use the unique properties of these directionals, the way they show up in the text, to search for what I want. So what I'm going to do is I'm going to use this sort of big, messy direction pattern. Let me walk you through it. This says, first, I want to match a space. The reason for that is a directional is never the first thing in a street address. There's always at least a number, like 512 Northwest. This means it will always be preceded by a space. This lets me rule out things like the N in the middle of Thorndike. It's not preceded by a space, so it's not going to go and find it. This would still make me find space Nickerson here, so I'm going to have to figure out another way to deal with that. I then say, I want to find any one of these things. This is what the meta character of parentheses, this is what it's for. It allows you to make sets of things where you could get one thing out of that set. Technically speaking, it says it has to make a match for everything inside the parentheses together, but the or means give me one of them. So this says, I want to match this entire contents of this, which is north, or northwest, or northeast, or south, southwest, southeast, west, and east. I'll accept any of these things. And then I will accept either a space following the directional or $, the end of the string. Basically, this is going to mean in Northwest, it will match the space after it, but in West, it will match the end of the string, but it won't match something like the N after Nickerson because it's neither the end of the string nor a space. Okay. If I run this direction pattern on my addresses, it extracts the space West on Thorndike Avenue West and the space Northwest space right here, because it's extracting everything it matches. It doesn't just match the letter, it matches the spaces too. And then it fails to make a match here or here, so it returns nothing because it's extracted nothing from this. Okay? Does that make sense? Question, are regexes length 1 vectors? Yes, they're always a length 1 vector. Can you explain the $ part? Yeah, the $ is just the same thing basically as the caret from earlier, except it finds the end of a string. So basically, if you put a $ there, the $ would occur at the end of your regular expression, and it will mean everything preceding it must be at the end of the string. Okay? So here's a question. Can you explain why it didn't pick the N in the last vector, as in the last element here? Yeah. The reason it didn't is because this expression says find the directional here, but it must then be followed by one of these two things, the things in the parentheses, which is either a space or a $. Well, this N is followed by an I. An I isn't a space, but it's also not the end of the string. The end of the string is over here after the T. It doesn't match either of those things, so it can't match the N. Did that answer all your questions? Oh, and why is there a blank after Northwest here? Well, the reason for this is if you see Northwest is sitting right here. When I use this regular expression, it's searching for a space here and a space here. Well, it ends up matching the space, the Northwest, and then the space here. So it returns everything I searched for. It just so happens I'm actually searching for the spaces, so it gives to it. So a question there. So the double parentheses automatically just means both. So kind of, what it's actually saying is this is a set of things here, and this is a set of things. If there's a bunch of ors inside the set, it only needs to find one of them. Same thing, it only needs to find one of them over here. If I don't have the parentheses here, it's going to assume I want to search for this, or 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 this. But the problem is it's going to say, or this, or this. Right? I want to get one of these and one of these. I don't want to just get this entire thing or this thing, if that makes sense. It's kind of like order of operations a little bit. This is a totally separate thing from this. So do everything inside, make a search, and then finish there, and then search in here, but they're totally separate. The next question, what would be the most elegant way of getting rid of the output's extraneous blanks? String trim. Probably is the simplest way to do it. String trim afterwards. Technically speaking, I could say using a much more complex regular expression, match but discard the space afterwards, but it's a pain in the ass, and so I don't bother, I just string trim it. It's a type of lookup that's really annoying to do. Great question. Why does the outcome show W or in W instead of true? That's the difference between string extract and string detect. So what string extract does is it pulls out the substring that matched the regular expression. So instead of returning a true, it takes out only the little portion that matched. So as a nice example of this, I'll throw this in. Show it at string view. So if you look at the string view over here shows that I matched space W and space NW space, which is what string extract returns. It actually just returns the exact thing the regular expression matched to. Does that make sense? Sorry, it's a little small. I have no way to increase the size of the viewer. Is that good? Okay, it's still confusing too. Regular expressions are sort of like a weird thing to wrap around, and you get better at them mainly by playing with them rather than listening to me gibber about them for an hour. Like most things, really, but you know, have to justify my paycheck somehow. Okay. So, anything else? Did I miss anything? Many questions. Why is there a space between before west and northwest? Yeah, absolutely. The reason I have to put so you're saying why is it returning the space? The reason for that is, again, that I searched for it and it returns what I searched for. If I search for a space, literal space here, it's going to return exactly what I searched for. Yeah. Thanks for asking the questions too. I want to make sure you totally get this stuff, so don't feel bad about stopping me for these questions. Okay. So, next one. Let's make use of this thing I just created or just worked with. I'm going to figure out where in Seattle all these different restaurant addresses are. So I'm going to say, take the restaurants in the data, reduce it to the distinct addresses in the data. I don't want to duplicate restaurants. Create a new variable, which is the city region. This is going to be equal to the result, as was suggested earlier, of running stringtrim on the result of that string extract function from earlier. The stringtrim will get rid of the extraneous spaces at the beginning and the end. Then I'm just going to tabulate the city regions and show you them in descending order. What this indicates to us is most restaurants in the data are in the Northeast region, which makes sense. It's the largest section of Seattle, followed by South. NA is the center of the city where there's no directionals. North, Southeast, Southwest, East, Northwest, and West. Okay, so we've used this to create something moderately useful. Okay, and as was suggested earlier, it's really common to string extract something with a space and then trim out the spaces. It's the easiest way to do it. Okay, so let's start getting more complicated. So maybe we want to do something like a street level analysis of our inspection data. That is, we want to do something like compare University Way with Pike Street, right? So what we want is we want only the street out of these big long addresses we have. So the question here is, how do we remove the building number or the unit number kind of thing, right? So if we have something like 2812 Thorndike Avenue West, what I want is Thorndike Avenue West, right? I gotta hack out the 2812. But we have things also like First Avenue. If it's First Avenue, I just want the whole thing. 10A First Avenue, I also want to get First Avenue. 10-A First Avenue should also give me First Avenue. 5201-B University Way Northeast should return to me University Way Northeast. And for some reason, this is a thing, 7040 and a half 15th Avenue Northwest should just give me the 15th Avenue Northwest. Okay. So I need a regular expression that will do this for me. Before I walk through this complex expression, you see it up here at the top. It should look like gibberish because it is gibberish, but we're going to walk through it carefully. I want to show you that it works. I get Thorndike Avenue West, First Avenue, University Way Northeast, First Avenue, so on and so forth, okay? And I'm doing this with this string replace. What string replace says is, give me the text, my number examples, run a regular expression on it. Anywhere you match that regular expression, replace it with something. In this case, I replaced it with a blank, thus deleting it. Okay, so this is a way to remove something you don't want from your string. Basically, this is the opposite of string extract. String extract only gave me what I matched. What this did is deleted what I matched. There's also a shortcut to do this called string remove. String remove, instead of having replacement, just defaults to deleting it. Otherwise, it works exactly the same. Okay, now let's walk through this mess of a regular expression. Okay, how does this work? Let's break it down. So the first thing we have here is we have this. We have a character a square bracket 0-9 square bracket. Okay, so what this says is, well, it's got a caret. The caret means we're going to start looking at the beginning of a string. So basically anything we're looking for, no matter what, it must be at the beginning of the string. Okay, then square bracket 0 to 9 means look for any digit, any numeric digit between 0 and 9, which is every numeric digit. So what this is going to do is it's going to match every number, at least single digit number at the beginning of a string. Okay, so if you've got 5201-B, it's going to match the 5, right? It's at the beginning, it's the single number. Thing is, though, there's probably more than one number. We want to match a bunch of them. So asterisk here means match potentially more digits. The asterisk means this thing can be there once or it can be there many times. Okay, so this is an arbitrary number of numeric digits ahead of time. So if I have 5201-B, this will match 520 and 1 because they all are a number between 0 and 9. Okay, next thing. Some addresses, for some reason, have dashes in them. I need to match them if they are there. So I say match a hyphen, but most addresses don't have it, so I put a question mark after it. This says you can optionally match a hyphen, but it doesn't need to be there. Okay. The next thing I say is, because there are things like 5201-B, they all seem to be single letters, so I want to match one of them. So I say, let's match any letter A through Z and make it optional. So if the address is just 5201, it will match it. But if it's 5201-B, it'll match it. But because the dash or the hyphen is optional, this would also match 5201-B without the hyphen. Okay? But it won't match a space, so it won't do something like 5201 Broward or something like that. It won't match the B in Broward because it won't match the space. Okay? And again, it's optional. So these two components, the dash and the single letter, are optional. So here's a question. What's the point of to 9 if we already have the X? Or the asterisk if we already have 0 to 9. So the thing is this is a set of numbers. This is basically saying the numbers 0 through 9. This asterisk just says repeat these things over here. If I just put 0 in here, it would match one or more zeros. If I put 0-7, it would match one or more numbers between 0 and 7, but it wouldn't match 8s or 9s. This actually says all the numbers from 0 to 9. Yep, exactly. You could say 2 to 9, meaning matching numbers from 2 to 9, but not 0 or 1. Yeah. That makes sense? Okay. Yeah. So next thing, we want to match a space. So one nice thing is all of those street numbers, the 5201s, the 5201-Bs, the 5201-Bs, every single one of them is always followed by a space before we get to a street name. So I always match a space. But because addresses are stupid and they annoy me, sometimes we must match a 1/2 because that's a thing that appears in Seattle. So I say optionally match 1/2 and space. So you'll see by putting them in parentheses, it makes the optional part affect the entire statement. So this is a reason to use parentheses. It says the entire thing here is an optional statement, which is 1/2 space. The thing to note, forward slashes are not a meta character, so you don't have to escape them, but backslashes are. This is just a thing. Okay, so you'll notice something about this. This is optional, this is optional, and this is optional. The only things that are not optional here are it must be the beginning of the string, it must have at least one number in it, and it must be followed by a space. Everything else is just special cases. So if I was doing this myself and I was writing this regular expression, I probably would start with this saying it must be at the beginning and it must be a bunch of numbers. And then everything else I add on over here is because I keep finding things that mess with my regular expression and I keep adding on to it. This is an iterative process. I didn't write this entire thing in one go and get it right. Absolutely. So square brackets are for identifying sets of things. So it's saying that there's special instructions here. Inside of square brackets, 0 to 9 says this is the numbers 0 through 9. If I put it in parentheses, it would literally be searching for 0-9. So the brackets are a thing to say the thing inside is some weird set of stuff, which could include things like there's actually I think it's :alpha num to get any alphanumeric character. All sorts of things like that can go inside those brackets to get sets. So brackets are for sets of things like A through Z. Parentheses are for a literal set of, like a literal things that you want to group together. So think of this as a group of stuff. Think of this as a special set with a command. Yeah, it's kind of hard to explain. How would it be different if I took out the asterisk? Great question. If I take out the asterisk, it will only match a single number here. So this would get me every address that has a single number. So 0 through 9 followed by a space or a -A, -B, but it would only give me one number. So the asterisk basically says repeat this as many times as necessary to make the match. Okay. Moving on. So now let's actually remove those street numbers. So I'm going to say here, take my restaurant's data, and then mutate a street-only variable, which is the result of string removing from the addresses my number pattern, which was my street numbers. If I get the distinct streets, I can see I get things like Southwest Avalon Way, Mercer Street, and damn it, Fairview Avenue North, Unit 1700A. I scroll down and I've got 112th Avenue Northeast, number 125. Whatever this is, Northwest Gilman BLC-08, Street Suite 300. Okay, I've gotten rid of my building numbers, but I am now plagued by a new enemy. My enemy are now unit numbers, which must be removed. Okay? So here's a question. If you want to search for a 3-digit number, what do you have to do? 1 to 9, 1 to 9, 1 to 9. You could do that, or you could specify I want exactly 3 digits. And I forget offhand what the syntax is for just saying 3 digits. It's like 1 to 9 followed by, God, is I forget if the 3 would go in front or behind or in the set. I actually can't remember. But there's a syntax for it. You have to Google it. Don't do it often enough to need to. And because of that, I would probably write it that way for a 3-digit. But if it was like a 9-digit number, I'd definitely go get the shortcut syntax. Okay. So our next thing is I must destroy my new enemy. My new enemy are the unit numbers. Let's see how we get rid of these. Okay. So getting rid of these is tricky because there's a lot of different ones, all of them stupid in their own unique way. A decent, what I call a decent attempt, is a decent attempt to make me feel better about my effort. A decent attempt would be to get rid of anything that occurs after the #, hashtag for you kids, suite, shop, or unit. Okay. So I'm going to say I want any of these things, but then I want to delete literally every, yes, Octothorpe. That's where, there we go, old school. I want to get everything that occurs after these. So delete this plus everything after it. Okay. So the pattern I'm going to use for that looks like this, and I think I'll explain it on the next slide. Things that I want to get rid of are things in this. I want to be able to match things like leave alone First Avenue, but Rainier Avenue South. This is a thing in Seattle addresses. What is number A? Really? This just, it's, anyway. Font the Right Way, Southwest Suite 108, number 100C, leave this alone, right? This pattern here seems to do a good job. With my test ones, it gets rid of the things I don't want and leaves me with my clean streets. Again, I'm just using string remove for this. Let's walk through this pattern right here and explain what it's doing. Yeah, that's actually read a sharp. Us band kids. Okay. How'd the unit regex work? Okay, so let's break it down. The first thing is every suite number, every unit number, all these things are always preceded by a space. So I'm just going to go ahead and say it must begin with a space. Okay. Next, I want to match any one of these things. So I want to match a sharp, a suite, a shop, or a unit. Any of these are good. Okay, so any one of these. But the thing is, what do I want to do? I want to match any one of these things, and I literally do not care what occurs after this. Yes, it's probably going to get some things I want to keep. Maybe there's some business name, something clever, like, oh, Suite 101. It's actually my old barber. Suite 101 or something like that. It's going to delete the suite and the 101 and leave me with nothing in the name. Whatever. But I'm not working on the names. I'm working on the streets. So hopefully it's not a thing, right? Hopefully there's no streets named shop, unit, or suite. Okay. So what we want to do, so a question, what's this? This is a literal character, so it's actually going to match this symbol in the text. This doesn't do anything special. Okay, so if I match any one of these things, I then want to match anything that occurs afterwards, no matter how many characters there are. So what I say here is period, asterisk, $sign. Period is a meta character. Period matches anything. Any character is matched by period. Okay, so this says match pound, suite, shop, or unit, and then any character that comes after it. And this includes spaces, numbers, letters, special characters, whatever, to match anything. I then say asterisk. So this says match literally any character, literally as many times as imaginable. If there's some data entry in here and one particular street is like unit followed by the entire contents of the dictionary afterwards, it's going to match the entire thing after unit. Okay, so we would have successfully taken the dictionary and deleted everything that occurred after the word shop. Okay, it would do it and it would work. Okay. The thing is, though, is I only want to match and delete anything up to the end of the string, which makes sure this entire thing is anchored to the end of the string. So no matter what I delete, it must be the last thing in the street. Okay, this is just a careful check to make sure I'm not deleting something like suite at the beginning before the directional or something. Okay. Yeah, so delete all that. Okay, that's all it does. Questions about that? If a period looks for everything, why do you need that? It looks for one of everything. So the idea is that we'll look for any single character. The asterisk then says, okay, any single character, any number of those things. So the asterisk is just sort of modifying it to be more than one. Anything else? There's also a plus sign, and plus sign would repeat the same exact match repeatedly. Good for looking for duplicates. When we're working in big data, I feel like it would be hard to find unusual failures if they weren't early in the list. Is there a way to tackle this? Yeah, so what I normally do is I essentially, I filter against things. So what I would normally do is, like, let's say I extract and clean up with my regex, then I use a different regex to find potential sort of failures or things I wouldn't expect. Like once we've done this, I wouldn't expect to see any numbers, you know, in the last like 5 digits or something like that, 5 spaces. So I'd substring out the last 5 and look for any number, stuff like that. You often need, there's more art to it than science, but you just got to come up with things. You're like, well, what would break this? Any experiment with it. Another thing to do is you do lots of random samples. Like I'll really quickly draw like random samples of 50, just enough to display on the screen, and just hammer it like boom, 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 over and over again. If nothing pops up, might be good. Yeah. So yeah, asterisk is normally the wild card, so this is a little confusing. Yes, it is. It's sort of kind of weird. So you'd expect this to be look for anything, but regular expressions don't obey normal human laws. They're like birds. Okay. So moving on. Let's do it. So now I say, take my restaurant's data, mutate the street only to be the result of string trimming. I want to get rid of extraneous spaces. String removing my original street only based on that pattern. Then I look at distinct streets and I get this. So I've cleaned off all my unit numbers. I didn't know what this was, so I left it alone. Northwest Gilman BLC-08. I actually searched for this. It's apparently in Renton, and it was still ambiguous exactly what it was, so I just left it alone. Okay. I think it's actually a unit in a strip mall. And so I think the C-08 should be gotten rid of, but I didn't know about the BL. Okay. Anyway, so if this was serious work, you'd probably want to get rid of the C-08. Okay. Okay, so let's do something else. Let's say what we want to do is I want to find where in the city danger lurks. By that, I mean what streets in the city have the most 45-point inspections. So what places have tragically high inspection scores? So I'm going to say here, take my restaurant's data, filter down to inspection scores greater than 45. Get only distinct business IDs, dates, inspection scores, and the streets. Count down to the streets only. So I'm counting the number of, basically this is the number of unique inspections that had 45 or higher. So the same restaurant could be represented multiple times. Arrange descending. And what we discover is danger lurks where all the delicious food does. So I'm not going to stop going to these places. So the answer is University Way Northeast has 108 different sort of events of getting massive violations. South Jackson Street, I'm not going to stop eating in the International District. Pacific Highway South, all the tasty stuff on Aurora, especially like the good stuff a little bit further up north in Aurora, Indonesian food and stuff. Northeast 24th Street, 76 of them. That's like Lake City Way, I think, or something. And Rainier South, good food down there in like the Southeast. I'm not going to stop going to any of these places. So this has conveyed no useful information except making me feel guilty for my decision. But if you want to know about it, I got it right there. Okay. If you do the mapping homework, the optional mapping homework, you'll find that I think in the data I've provided, the worst inspection score in the entire data set is the kitchen in a fraternity on frat row. It had, if it's the same data as before, it's got like 70 violations or something like that. Can you even imagine what that looks like? It must be apocalyptic. Anyway, so probably like the rest of the inside of the building. Okay, so some other things. You might want to split up strings. If you remember back in week 5, I used the separate function to take like one column and split it into 2 columns. Sometimes what you want to do is instead split up into lists or split up into a matrix and maybe extract one side or the other. You could do this with the string split functions. For instance, string split fixed will take some string, like here I've got the violation descriptions. I say I want this split up by space hyphen space, which is how they break up the number of the violation, like the code it is attached to, and the actual violation. I want it split into 2 pieces. This would give me a matrix where the first column is the first thing on the left side of the split. The second column is everything that was after the split. So for instance, code violation 4100 is where washing facilities properly installed. So improperly installed where washing facilities, blah, blah, blah. Okay. So might want to use that, kind of speed along. Here's another thing I added kind of recently. Maybe you got something like you have a report or a website and you need text dynamically generated from data, but you actually want to make like whole sentences or something like that. I'm going to give an example of that. Something I do here, doesn't matter what I'm doing here. I'm just prepping some recent scores so we can use as some examples. Doesn't matter what I'm doing here. Okay. What we could do if we want to assemble sentences out of our data, we could use paste to string a sentence together. So for example, here I'm going to say, I'm going to take the recent scores data and mutate a text description. What I'm going to do is paste together the name. I'm going to say the name of the restaurant is located at this address in this city and received a score of its inspection score on the month that it had its inspection done, the date it had the inspection done, and then a particular year for the inspection. And then I can select only that column, and I've written out sentences like Supreme Bean again is located at 14424 Ambon Boulevard Southwest in Burien and received a score of this on this particular date. Okay. A thing about this is it just kind of runs off on the right. It truncates it due to the output. I might want to display this in my console to see. So I could modify this with some line breaks, which I'll show in a second. Another way I could do this, instead of using paste, is using the glorious glue package. We could use string glue, which is a sort of alternative to pasting things that's in Stringer. This uses the glue package, which allows us to use sets of strings that have variables in them instead of separately listing the strings and the variables. This produces the exact same result, but now I write it like this. Instead of saying paste together a variable, some text, a variable, some text, I instead just get to write my sentences out. I say string glue together, squiggly bracket name. This is going to replace this right here with a value from the name variable. The name is located at address in city, space, and I can just put commas here wherever I want to break this up. They're not meaningful. This just lets me write them on multiple lines nicely. And received a score of inspection score on month when, and you'll see I can actually do a function call inside of here. It will run the function, process it, and spit the result out, and run all this stuff for me. I get the exact same result here. If you're going to be writing long sentences inside a call like this, glue is a little bit nicer syntax for doing it. It works basically the same way as this previous thing, but it's just a slightly nicer syntax. If you find this confusing or hideous, dismiss it from your brain forever. You don't need to use glue. I find the syntax a little easier. How do you get it to return that character there? I think you just escape it. So put 2 backslashes in front of it. Actually, maybe in this case, it's 1 backslash, now that I think about it. Yeah, I know, exactly, right? If it's not the regular expression, I don't need the double backslash. Okay, so anyway, so maybe what I want to do is I want to do these sentences, but in my console, I want them to be shown with line breaks. I can add line breaks to this, okay? So if I want to do that, what I can do is I can give some text to the string wrap function, or manually insert \n. \n is the line break character. It will make a return, a carriage return in your text output. So what I'm going to do is I'm going to take the score text data I created earlier. I'm going to pull out those text descriptions. So this is now a vector of them. I'm going to say string wrap them. So the sentences, that is the individual lines, are 70 characters wide. And then between them, I want to print out a double line break and then concatenate the output. This is going to take the entire vector of all my sentences and write them out 70 characters wide, which is coincidentally the width of my output frame in these slides. At the end of 70 characters, it does a line break and keeps writing it. When it gets to the end of a given entry, it does 2 line breaks, so a line break here and a line break here, and then goes to write more text. So what I generated was stuff like this. Mandarin Garden is located at 40 East Sunset Way in Issaquah and received a score of 72 on March 9th, 2007. This is dynamically generated text from my data frame. Okay, so here's a question. Can we delete period in the code unit pattern there? If you wanted to, do you mean delete the period from that pattern, or delete the period from the text, the resulting text, like if there's a period in it? Do you mean, do I need that period? We definitely need the period, because the period says match anything after unit shop suite, or pound sign, and the asterisk then says repeated multiple times. Without that, we wouldn't delete the things after those.
I got you. Thank you.
Yeah. Okay. So anyway, this is how you might generate text dynamically. Kind of handy. Okay. One last slide here is basically, here's some other useful functions might want to use. I don't show them here. String pad is for adding spaces or other things back. If you have zip codes that were read in numerically, you need to add the leading zeros back. You could say string pad your zip code. Their width should be 5 characters. Add things to the left, add a 0. That would be string padding out, adding zeros back. It's good for adding numbers back to ID codes that were dropped leading zeros to. String subset will return all elements that contain matches of the pattern. So instead of extracting part of it, it would give you the entire thing that matches. So you give it a string, the pattern, and it won't just return what it matches, but the whole element that contains any match. String which returns numeric indices of elements that match, so you know which number they are instead of just trues and falses. String replace all will do multiple replacements inside of a string. And string squish will trim duplicate white space inside a string. So if there's 2 spaces in a row, it will remove one of those spaces, squish things down to remove duplicates. Okay. Your homework is the second part of homework 6, due next week, all the usual jam. We'll cover it in lab like usual. We'll walk through it. One question down here. Do regex work on non-Roman letter languages? Yes, absolutely. You may have to give them Unicode values for those languages though. So you might have to do something like pull out, the Unicode values from which would be a slash and a hexadecimal string, but they will work with it. So could you say again, paste 0/n/n? Yeah, so this is adding 2 line breaks to the end of each one of these sentences. So basically, the thing that resulted from these lines of code was the sentence up to here. But if I just concatenated them, it would immediately start with Mandarin Garden here. By adding /n/n, it did 1 line break and then another line break to put this 2 lines below the end of this sentence. You could remove it and see what happens, and you'll see immediately what it's doing. Okay. Anything else? Okay, well, that's strings. Useful stuff. Practice with them. Don't try and memorize all the stuff, but it's useful stuff for working with textual data. Okay, and if you have ever have questions on regular expressions that you just can't figure out, do feel free to shoot me an email or a message. I can at least point you in the right direction. Usually I find them fun enough puzzles that I just do them, but we'll see.
Thank you, Chuck.
Absolutely. See you folks on Monday. And have a happy Thanksgiving or quarantinesgiving, whatever people are doing. Sadly, eating a turkey microwave meal and drinking an entire bottle of wine, something like that.
Thank you, Chuck.
Yeah.
Thanks.
Thanks.